So far, we have only looked at including quantitative data in our regression models. However, we may wish to include descriptive or qualitative data as well. For example, we may want to include the gender of the respondents in our data if we think the gender of the subject has an effect on the person's pay, or does one's life expectancy depend on their zip code. Both of these are examples of studies that have been published. Both gender and zip code are examples of categorical data. Recall that even though zip code is a number, it is not a numerical value. It doesn't represent a quantity. It presents a category. In this lesson, we will learn how to incorporate categorical variables in regression analysis. Categorical predictor variables cannot be entered directly into regression model. We have to take an additional step before being able to run the analysis. Let's take a look at the obesity calculator again. I shared this with you in the last lesson. In this study, they had several categorical variables, such as gestational smoking, which could take on a value of a yes or no, or the maternal professional category, which could be one of the 4 given choices. These variables first need to be coded such that their meaning is represented by a number. To do this, we create a dummy variable. A dummy variable always has a value of either 0 or 1. For example, if the mother smoked during the pregnancy, then the dummy variable will have a value of 1 and 0, otherwise to represent yes or no. And of course, when a variable has more than 2 possibilities, as it is in the case of maternal professional category, the use of dummy variables will require a little bit more work. For now, let's start with the example where there are only 2 possibilities for the indicator or dummy variable, and later we will learn how to use dummy variables when there are more than 2 possibilities. A published study of male and female nurses in the United States showed that pay inequity was present between male and female nurses. What this study found was that the gender was an explanatory variable for predicting a nurse's salary. Let me use a simulated data that we can use to show how we could check on the correlation between gender and pay. We collected at random salaries of 120 male and 120 female nurses. We also have identified length of experience as an explanatory factor for the salary. We now want to see if gender has played a role as well. So here, variables are for Y, it's salary that's being predicted. X1 is experience recorded in months. X2 represents gender, which is categorical and has 2 possibilities, male or female. This is just a small snapshot of the data we have. The data here shows the month of experience and salaries of males and the female nurses. Before we can run regression on this, we have to code each male or female nurse with a numerical value of 0 or 1. We can create a dummy variable to represent each gender. For example, I can have a dummy female, which I can set to 1 for a female nurse and 0 otherwise, and a dummy male, which is equal to 1 for male nurses and 0 otherwise. But is this really how we should do this? The answer is no. And let me explain why by explaining what is known as a collinearity. In multiple regression, collinearity occurs when one independent variable is highly correlated with another variable. When this occurs, we have to remove one of the variables from the model as not to violate the independence assumption. The way we created our dummy variables in the last slide for our nurse's gender will cause collinearity, and this is why. If dummy for female is 1, then it means that we are looking at a salary that belongs to a female nurse. Then for this subject, the value of dummy male must be 0. So if we code the nurse's gender this way, the 2 dummy variables will be completely correlated and violates the independence assumption. To do this correctly, we will create just 1 dummy variable to represent the nurse's gender. I am going to call this D sub G, D for dummy and G for gender. I am now going to set the value to 1 if the nurse is a male nurse and 0 if the nurse is a female. The table you see now is a snapshot of what the coded data will look like. Now that all the values in the data set are numeric, we can run the regression analysis. First, we get a very good model. The explanatory variables included in the model explain 94% of variation seen in the salary data. But are both gender and months of experience significant? For that, we will look at the bottom table of the output and focus on the p-values of these variables. Both variables have very small p's, which implies that they both have a significant relationship with salary. So now let's see what all of this means. In a perfect world, gender should have no effect on the salary, but here we saw that it had, such as life. Based on this analysis, what can we say about the pay gap then? The coefficients of independent variables, along with the intercept, make up the regression equation expressed as you see here. Recall that x1 represents months of experience. This can be any number depending on how long the individual has been a nurse. The other variable in the equation is x2, gender, and this is the interesting one. This is the one that has only two possibilities. This variable is equal to 1 if the nurse is a male and 0 if the nurse is a female. In order to understand the coefficients for gender variable, ask yourself what will happen if we wanted to predict salary for a female nurse. Since the gender variable is 0 for female nurses, then that part of the equation gets eliminated, and this will be the equation for the female nurses. And for male nurses, x2 is 1, and the last coefficient is multiplied by 1. Do you see what just happened? By multiplying the last term by 1, we just gave all the male nurses a constant salary bonus of $4,667.70. Now let's use the equation. We have two groups of nurses. Both groups have on average 10 months of experience. One group is all male and one group is all female. What is the estimate of average salary for each group? Placing 10 in x1 and 0 in x2, predicted salary for female nurses will be about $61,972. And placing 10 in x1 and 1 in x2 for male nurses, the expected salary for male nurses is about $66,640, which again is the $4,667.70 more than the female nurses. So the coefficient for gender variable shows the difference in the salary for male nurses from the female nurses. In this case, there is an added gender bonus of $4,667 for males. The takeaway here is, for all models that have categorical data with two possibilities, the coefficient for dummy variable shows the deviation of the prediction for the category that is in the model, that is coded as 1, from the category that is left out, that is coded as 0. So let's practice. What do you think would happen if I had done the coding the other way around? For x2, that was for gender, I would have said x2 is equal to 1 if it's a female nurse, and x2 is equal to 0 if it's a male nurse. Adjusted R square is the same as before. What changed are two coefficients. First is the coefficient of gender. Value-wise, it is the same as before, but now it's negative. So a female nurse gets a deduction of $4,667.60. But there is another coefficient that has changed as well, and that is the coefficient of the intercept. I'm guessing you didn't see this coming. Let me explain what just happened. The intercepts are different when we look at the two different ways of coding the gender. The best way for me to show you what just happened is by just subtracting the two. And you see that the magic number of $4,667.70 gender effect reappears. This is the estimated starting salary of a female nurse. And this is the estimated salary of male nurses, which is $4,667 more than the female nurses. Now that you see the numbers, let me explain the principles of it. The coefficient value of intercept is the value of y when all the independent variables are set at 0. All variables being 0, in this case, would mean this nurse is a new hire and is a female nurse. Female is equal to 0. Thus, the intercept in the model, when we code the dummy variable as 1 for male nurses, shows the starting salary for female, and that would be $61,149.40. And it would be the other way around when we code female nurses as 1. Could we have done this study by hypothesis testing between the two groups? The answer is yes, but regression gives us more information than just the ability to reject the null hypothesis that male and female nurses have equal pay. Regression allows us to isolate the effect of each variable. So in this example, we were able to, in one shot, isolate the two sources of variations for differences in pay, experience and gender. And we can say that collectively, they explain 94% of the variations. If we want to know how much of the difference is explained by just gender, then we can run a simple linear regression with just the gender dummy variable. And I did just that. I ran the analysis with only gender, so I get this summary output. This was ran as a simple linear regression with just one independent variable. So looking at R-square, I see that about 33% of the salary variations are due to gender. Regression not only is a great predictive model, but it's also a great way of isolating the variables that influence our variable interests, in this case, salary. By knowing this, we can then set out to change the independent variables so that our outcomes are better for us. These are why we exercise, eat nuts, get rest, etc., etc., because someone has done the studies that show exactly what and how these variables affect our health. It is no different in business, and we can harness this power from this very powerful statistical tool to improve business outcomes.